Hi, I'm Fabian. I'm going to talk about our work in efficiently pre-processing large video datasets for video analytics tasks. Video analytics is becoming more and more useful for more and more applications. We have lots of different kinds of videos out there that are useful to analyze, like traffic camera footage, sports footage, and video of wildlife, and there's a correspondingly diverse set of applications that can benefit from that analytics. Like for traffic cameras, we can do various traffic planning and traffic safety analysis tasks. Ecologists are often interested in studying wildlife video to study different kinds of animal behaviors, and sports analytics is, of course, a big domain as well. Now, many video analytics tasks involve object detection and tracking. And object detection is just the prediction of the bounding box position of an object in one frame of video. So for example, here are a bunch of detections of cars shown by the colored bounding boxes. And tracks are just sequences of detections, the position of an object over the segment of video in which it's visible. And here's two different representations of the track of the same van. And yeah, many video analytics tasks involve detection and tracking. And oftentimes, once we have object detections and tracks, the task itself is relatively straightforward. So for example, let's say we're interested in a traffic planning kind of application where we want to compare the frequency at which cars run red lights at different traffic junctions throughout a city. We can, if we already have tracks of red lights and of cars, then we can find cars that run red lights just by looking for cars that go straight through the traffic junction while the light is red. So you can see that once we have the tracks of the objects that are relevant to this kind of task, actually doing the final post-processing to achieve the task is not that complicated. The issue, though, is that object detection and tracking methods are very compute intensive, especially if we are applying the most robust methods that use deep convolutional neural network models. For example, a popular object detector, YOLO v3, runs at just 100 frames per second on a $10,000 GPU. And what that means is that in the cloud, it's going to cost about $1 to process each hour of video. So if we have a large video dataset, like 1 month of video from maybe 100 cameras, then that would already cost $72,000. All right, so that was a bit of motivation. Hopefully now I've convinced you that there's a lot of useful video analytics tasks, that many of these tasks involve object detection and tracking, but that accurately detecting and tracking objects is compute intensive. Now I'm first going to talk about some prior work in addressing the compute intensiveness of these kinds of analytics tasks, and specifically I'm going to talk about video query optimization systems. So the naive way to solve some of the tasks I've talked about would be to take our video dataset, apply object detection and tracking models on it, and get out all object tracks of object types of interest from the video. Then once we have the tracks, we can run a bunch of different video analytics tasks over those tracks without needing to do any more video processing. So this last step, where we just do the task given the tracks, is generally straightforward and also not very compute intensive. The problem, of course, is that actually getting those tracks can oftentimes be cost prohibitive. Video query optimizers try to turn this process kind of on its head, where now we start with the query, the specific task we want to perform, and the video query optimizer looks at that query and comes up with a specialized query plan that figures out what the bare minimum work needed to answer that specific query is. And so now instead, when we're processing the video, instead of processing it in a very general purpose way to get out all tracks of objects of interest from the video, we're just going to do very query-specific minimal video processing. This works very well when we have just one query that we want to answer about a large video corpus. But in scenarios where we have many repeated queries, like in ad hoc exploratory analytics settings, it starts to make less sense, because every additional query is going to incur a linear increase in the execution time because we have to keep doing more and more query-specific video processing over and over. And so what actually makes more sense in these settings with repeated queries is something closer to the naive approach, where we take our video, we do this general purpose object detection and tracking to get all tracks first, and then we can answer a whole bunch of queries in just a matter of seconds once we have those tracks. But we're going to need to heavily optimize detection and tracking in order to make it not cost prohibitive. And that's exactly what we do in OTIF. And the key idea in OTIF is really to optimize detection and tracking by essentially combining as many optimizations as possible into one cohesive system. So we're going to optimize speed along multiple avenues, from the object detector to the tracker to this proxy model component as well. So the OTIF tracker architecture consists of a bunch of these components, 3 components in particular, that each expose parameters that can be tuned to optimize tracking performance for a particular video dataset. So we have 2 components, the segmentation proxy model and object detector, that deal with efficiently extracting object detections from individual video frames. These are those bounding box predictions of where objects of a certain type are. And we have this 3rd component, the recurrent reduced rate tracker, that deals with processing over segments of video and picking which frames to process through the detection pipeline, and also combining detections of the same object together across different frames where that object appears, and that's building the object tracks. So we do have these 5 parameters we need to tune, and the workflow to do that is really a sampling-based approach, where we take our very large video corpus, maybe tens of thousands of hours of video. We sample a validation set that in our implementation consists of 60 1-minute segments of video, so 1 hour of video in total, and then we tune the parameters essentially in that validation set of video. We evaluate runtime and accuracy on the validation set and see what combination of parameters works well. So I'm first going to talk about the tracker architecture in OTIF, and then I'll briefly discuss the parameter tuning at the end. So I'm going to start with these 2 components in the detection pipeline, first the segmentation proxy model. So one way to accelerate object detection performance is to reduce the resolution at which we process video through the object detector. The issue, though, is that the detector has a relatively difficult task. It needs to distinguish individual objects and predict bounding box positions for every single object. So we can't actually reduce the resolution that much. What we can do, though, at a much lower resolution, is just tell roughly where objects are. So we can have this fast segmentation proxy model that looks at a very low resolution video frame, and it doesn't distinguish individual objects, but just for every patch in the video frame, it predicts how likely it is that there is at least one object of interest in that patch. So it's a much simpler task. Now, if we are able to efficiently compute this patch level, how likely it is that there's an object in that patch kind of map, what we can do is skip object detector processing over portions of the video frame that we're very confident do not contain any objects based on the outputs of the very fast segmentation proxy model. So now we can just apply the object detector in these red windows, and we get the same bounding box predictions we would have gotten had we processed the entire frame through the detector. And that's the basic idea behind the segmentation proxy model, and there's 2 parameters that we need to tune in order to make this work effectively. The resolution at which we process video through that fast model, and the threshold that we use to convert its confidence scores in every patch of the image into a binary decision about whether or not we need to process that patch through the object detector. So for some frames, if there's no objects of interest, the proxy model might be very confident that there indeed is no patch that contains an object of interest, and then we don't need to run the detector for that frame at all. Right, so that's the segmentation proxy model component. A second component, the second half of this detection pipeline, is the object detector itself. And I was saying earlier that we can only reduce the resolution at which we process video through the detector by so much because it does have this relatively difficult task of distinguishing individual objects. But nevertheless, it's important that we try to do so, and so that's another parameter that we tune in OTIF, the resolution, along with this confidence threshold in the detector. The final component is the object tracking model, and that sort of sits on top of the other 2 components, managing which frames we sample for processing, and then combining object detections across multiple frames to form object tracks. And the key parameter here is the sampling gap that controls the rate at which we process video. So if we have a raw video file, we could process it at its native video capture rate, usually 25 or 30 frames per second, but oftentimes there's a lot of redundant information there, and we can get by, we can achieve the same accuracy by processing the video at just 5 frames per second, or for some video datasets, maybe even just 1 frame per second. And so that's really the main thing that we're controlling in the tracking component. All right, so that's the OTIF tracker architecture. Now let me just briefly talk about a bit more about the parameter tuning process. So we've already sampled this validation set of video, and essentially we're going to be profiling a bunch of different combinations of settings for these parameters in the validation set. So we'll get a runtime and accuracy in the validation set, and we have some sampling-based guarantees that these performance numbers are going to translate over to the rest of the data set. This is essentially a search process. I'm not going to get into the details of the search procedure we use, but essentially the output of the process is this curve that offers a trade-off between runtime and accuracy, and we would hope that we would get as close to the Pareto optimal curve as possible while using while not taking too much time to do this profiling of different combinations of parameters. And so once we have this curve, we can present it to the user, and the user can pick one point along the curve, which is every point along the curve is a setting of those 5 parameters. The user can pick a point and use those settings to process the rest of the video dataset. All right, so now let's look at some results. We compared OTIF against several baselines on 2 different types of queries, object track queries and frame level queries. Object track queries, I'm going to talk about those first, are basically any query that involves object track. So for example, if we want to count the number of cars that turn through all the valid turning directions at a traffic junction, that's an example of an object track query. And we compared OTIF to 5 baselines. Some of these come from the data management community, like Myris, Chameleon, and NoScope. Myris in particular is a video query optimizer designed to accelerate the execution of individual object track queries. And a couple of these come from the computer vision community and are more about accelerating general purpose object tracking, like center track. And we compared on a bunch of datasets, 7 in total, with different queries for each dataset. And 5 of these datasets actually come from prior work in video query optimization: Tokyo, UAV, Warsaw, Amsterdam, and Jackson. And we compare all of these methods in terms of their speed accuracy trade-offs. So here we have runtime on the y-axis, where lower numbers are faster, and accuracy on the x-axis, where numbers further to the right are better. And OTIF's curve is in green. And you can see that across all of these different datasets, OTIF is offering substantially faster runtimes at the same levels of accuracy. Now in our second evaluation, we compared OTIF against Blazed and Tasty on frame-level limit queries that Blazed and Tasty are really specifically designed to process efficiently. So an example of a frame-level limit query is select 50 video frames with at least 3 buses. Now, because Blazed and Tasty are these video query optimizers that try to do query-specific video processing for each query that they're given, we would expect OTIF to perform better than them when we have many queries that we want to run on each dataset. So for 5 queries per dataset, we see that indeed OTIF is quite a bit faster because it only has to do 1 pass through the video to do this general purpose object detection and tracking, whereas Blazed and Tasty keep having to revisit the video over and over for every additional query. In fact, after OTIF computes the object tracks, processing every additional query takes just about 100 milliseconds. Surprisingly though, even when we have just 1 query on each dataset, OTIF is actually already competitive with both Blazed and Tasty. In fact, it's faster than both of these baselines. And that's surprising because Blazed, for example, is designed to answer 1 query very quickly. It's doing query-specific video processing just to extract minimal information from the video to answer that 1 query, while OTIF is doing this much more general purpose object tracking of all objects that appear in the video. And the reason why OTIF is able to be faster is really because we're combining so many different optimizations, from the detector resolution to the rate at which we process the video to the also introducing this new segmentation proxy model approach. All right, so that's all I have. For more details, check out our website at the URL here.